Hello, this lecture will cover pages 186 through 188 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on flip-flops and related devices, Part G, using the 555 timer as an astable multivibrator. What I'd also like you to do is get into Canvas, and in Canvas under the course notes or course documents, you will see that I have provided a 555 specification. It looks like this. Here's the specification that you'll find. It's I think it's 10 pages. And I want you to have the specification out and handy as we go through this very brief lecture. I want you to read the general description. I want you to read the features and read the applications. This 555 timer, if you take a look at it here, this is our lab layout right here, and notice that these are all the chips we've been using so far, but I have a 555 timer that's sitting right down here, and I'm going to take it out. I want to show it to you. This is what it looks like. It's just a very small 8-pin package. And there's one timer in there, one 555 timer, and we can use it for many, many different applications. Inside this 555 timer here is this circuit. In your specification, all these transistors and resistors are all inside that little device right there. But all we care about is how we use it. So on the second page, you'll see the pinouts up here, and I'm going to set that right beside it. Pin 1 is ground, pin 2, pin 3, pin 4, pin 5 down here, pin 6, pin 7, and pin 8 is VCC. This is not like our standard packages that we used. We always had VCC here, and at the opposite end and on the other side it was ground. But no, ground is pin 1 with this package. So make sure you look at this dual inline view here of it, so before you use it in lab. So how can we use this 555 timer to design a free running oscillator circuit? Well, if you take a look on page number 186, and you can also look in your specifications at the application notes, which are back on page 8. Yep, they start in page 7. On page 7, you'll see in your application notes here that this is the monostable operation. It's the next lecture. But here's the astable circuit. If you want to connect this as an astable, free-running oscillator, clock circuit, this is the way you do it. And on the following page, I'm not going to turn it, but it gives you the equations that I'm going to give you right here. So this is what you need to know about the 555 timer if you're running it in a free-running astable circuit. You connect the circuit like this. Notice it has two resistors, RA and RB, and it has two capacitors. It has a capacitor C. The RA, RB, and RC are used in all your calculations. This 0.01 microfarad capacitor from 0.5 to ground is used as a stabilizer for the chip. So no matter how you use this chip in the astable mode, you'll take pin 5 to ground through a 0.01 microfarad capacitor. Notice that pin 8 goes to VCC. Pin 4 is a low active reset, so we just tie that high as well. Then we come around from pin 8 through resistor RA to pin 7, and then through resistor RB to pin 6. Pin 6 and 2 are tied together, and pin 6 goes through the capacitor to ground. If you connect this circuit up like this, if you take a look at your equations in your app notes, which I'll just draw right here for you, it's a lot easier to see, you'll get a free running oscillator circuit that looks like that. And the period obviously is going to be this T. There's T, your period. From there to there is your period. And this is your time high. I'm going to call this T sub H. That's your time high. And this here, from here to here, is your time low. And I wrote that all right here for you so you can see it in your notes, because that's how I use these in the equations down here. The time low is given by 0.693 times the value of RB times C. The time high is given by 0.693 times the quantity RA plus RB and the quantity times C. So obviously if you add these two together, you're going to get your total period. If you take the time low and you take the time high and take the time low and add them together, you get the period. So you just add these together and you'll see that the total period is equal to 0.693 times the quantity RA plus 2RB times the quantity times C, and that's in seconds. You invert that and it gives you your frequency. So here's a very important equation you're going to use a lot. The output frequency of this circuit is given by the equation approximately 1.443 divided by the quantity RA plus 2RB and the quantity C, and that's in hertz. We're going to define duty cycle the way we always have. It's the time high divided by the total period. Well, here's the time high. Here's the total period. You can put that over that and things cancel out, and you can see that the duty cycle is given by the quantity in the numerator RA plus RB divided by RA plus 2RB times 100%. Note that the time low and the time high, there's no way that the time low and the time high can be, they can't be equal to one another. The only way they can be equal to one another if RA is equal to 0. Or the only way you can get a 50% duty cycle is if RA is equal to 0. Because if you take a look at right this and RA is equal to 0, RA goes away and you have RB over 2RB, you get a 50% duty cycle. So these equations are only good from 51 to 100% duty cycle. You can't, with these equations, you cannot get, with this circuit here, you cannot get below a 50% duty cycle. And this is why, because RA would have to be 0 to get 50%. So we're going to have a couple homework problems to do with this, but basically you'll see them through examples here in a minute how we use equation A and equation B here. Note, like I just explained, as can be seen in equation B up here, you'll never get a less than a 50% duty cycle. Can't happen with that circuit. The best you can get is 50%, and you're approaching that because you just make RA much, much less than RB, and you can approach 50%. The only way to get, down at the bottom here, the only way to get a percent duty cycle less than 50% is to modify the circuit as shown and explained in examples 517 and 518 and on pages 270 and 271. It's the only way you're going to be able to do that. So what you're going to have to do is you're going to have to take a look at this part of your book here. If you just use this circuit right here, these are your equations, and your duty cycle is greater than 50%. But if you need to get less than 50%, this RB has to be replaced with RB and 2 diodes. In other words, this one component of RB has to be replaced with an RB plus 2 diodes put in the circuit this way. That's what goes inside this shaded area right here. These 3 devices here. And then these are the equations you use. That's the only way you're going to get 10%, 15, 20, 30% duty cycle. Now, in the lab, you can do it that way because you're going to have to build this in the lab. You'll see this in just a minute. But if you need a 20% duty cycle, what I would recommend for our application, rather than going through this extra work of replacing that value of RB with this combination here, is I would simply, if you want a 20% duty cycle, design a circuit for an 80% duty cycle and then use an inverter in the output, out here on the output. Think about that. If you have a duty cycle that's 80%, let me see if I can't draw something that approaches 80% here. Make something up here. I'm going to say that I'm going to say that that right there is an 80% duty cycle. I'm going to say that's what that is. That's an 80% duty cycle the way we defined it. If you take that and you run it into an inverter, what do you get out here? Well, you get this. Let's do this. If you run that through an inverter, you get this waveform. It's low, it's high, low, and high. So here you have your 80% duty cycle as the way we defined it, time high. And as you go through the inverter, you get your 20% duty cycle. Right there. So I'll allow you to do that if you want to do it. Page 187. We have a couple examples there. Example number 1, using the 555 timer as an oscillator, find the frequency and the percent duty cycle of the output if RA is equal to 3.36 k ohms, RB is 18 k ohms, and C is equal to 0.01 microfarad. Work that out just using these equations right here on the previous page, and you can see that we get a frequency out approximately equal to 2 kilohertz, free running oscillator, and the duty cycle 75%. See if you can't get that. But what if you wanted to work backwards? It usually doesn't work this way. Usually in your specification, your end user asks you to design a oscillator using a 555 timer with the following characteristics. They want like a frequency of 2 kilohertz and a percent duty cycle of 75%. So how do you work back to here from this specification? Well, as a starting point, I want you to use figure 6 on page 8 of the 555 timer specifications. If you don't use that figure, you'll have to design this circuit using simultaneous equations, as I show you for the solution in homework problem 546. Not difficult to do that. You just end up with two equations with two unknowns, and you work them out simultaneously. But I'll show you what they do in the specifications here. Let me grab page number 8 of the specs here. Okay, let me show you how to use it. Here is page 8 of the specs, and we're looking at figure 6 down here. Now, you're going to have to look very closely at this, because this is going to help you design this problem right here. Example 2 on page 187. First of all, forget about this duty cycle they have in these application information notes. They assume the duty cycle as a low, the time low. We defined it as time high. That's the reason their equation here is different. So we're going to forget about that equation. We're going to define it the way that I've defined it, for some time now. Your starting point here is figure 6 in this problem. Notice that these parallel lines represent RA plus 2RB. That's hard to read right there. But these lines here represent RA plus 2RB. And this abscissa or x-axis represents the free running frequency you want, and the vertical or y-axis represents the capacitance. So what do we want to do here? We want a 2 kilohertz. So if you look at 2 kilohertz down here, notice this vertical line here is 1 kilohertz. This vertical line here is 10 kilohertz. So, halfway in between is going to be 5 kilohertz. So let's be as accurate as we can. We can look here somewhere around 2 kilohertz, and we'll come up, and we could pick the 0.01 microfarad like we had in example number 1, but let's pick a different value to show you this works. Let's pick a capacitance of 0.1. So for a capacitance equal to 0.1 microfarad, RA plus 2RB, RA plus 2RB is equal to what value if we want 2 kilohertz? Well, these parallel lines represent RA plus 2RB. We come across here until we get to 2 kilohertz. There's the 1 kilohertz line, so we come out a little wee bit. It's hard to read this, and you go up, and you see where that vertical 2 kilohertz line would intersect the 0.1 microfarad, and it isn't going to be on the 10 kilohertz or the 10 k ohm parallel line there. It's definitely not going to be on that line. So you're going to have to like interpolate here some parallel lines and have another parallel line coming down through there. Notice that this parallel line is 100 kilohertz. This parallel line is 10 kilohertz. So another line coming through there, you know, parallel, I don't know, maybe that would be somewhere around 20K. Maybe it'd be around 15 or 20K to put it close to the 10 kilohertz line, but far enough away from the 100 kilohertz parallel line. Don't forget we're interpolating here. So let's say that's 15 k ohms. Let's say it was. So you're going to have RA plus 2RB plus 2RB is going to be equal to about 15K at that frequency. You know your capacitance, pick a value for RA. I don't know, make RB 5, make R sub B equal to 5K. If RB is 5K, RA has to be equal to 5K. Is that right? RA plus 2RB equals 15K. That's going to give you your 2 kilohertz. But the problem is you have to satisfy another equation. You need your percent duty cycle to be 75%. My definition of my percent duty cycle right now is percent duty cycle was equal to RA plus RB divided by RA plus 2RB times 100%. If you put those values in there, you're going to end up with 10 over 15. You're getting about a 68% duty cycle. That's not the 75 we want. So you have to go back and rework the value for RB, calculate RA, do a little trial and error. But that's the way the engineer would design going from a problem like this to get back to values like this. So make sure you know how to design an oscillator using a 555 timer with certain characteristics. Pick one. Pick a frequency equal to 50 kilohertz with a 60% duty cycle. See if you can't work it out, and then put in your numbers and see if those numbers give you these results. That's page 187. And on page 188 is where you need to do a design problem for lab. And in order to do this problem, it says you have to very carefully look over pages 269 through 271. So you're going to have to very closely look over what you need to do to get the duty cycle down below 50%. And secondly, if you read this section right here, very important section to read, talking about the intervals T low and T high and the overall period of oscillation. And there's your example 517. Example 517 gives you a pretty good idea of how to use the equations in general, but if you need to get below 50%, the bottom of this page here, page 270, right there, explains how to do that. And example 518 is a very good example to show you, in this case, how to get a 25% duty cycle. Hope you can find that in the book. It's on page 270, 271 here in the textbook I'm using. Example number 3, you have to get that ready for lab. And that concludes the lecture.